And physicists who start this CERN collider experiment? You are this first batch of people, of Indian people, who started the collider experiment at CERN. Yeah, so that's the point I'm trying to. I was not 100% sure. Yeah, so so that's why I'm saying that now to previous Monday you had a lecture. Previous day you had a lectures on the history of particle physics in India, and today we have been members who started this our collider experiment at CERN in way back in 1970s. Okay, so now Professor Gurtu, he was a faculty member here, and he retired in 2010, 11, and he worked in this. Okay, initial I also do not remember this ISR experiment. I don't remember exact name of the experiment, but starting from the ISR, he was in L3 experiment, and then he was the person who started the India CMS collaboration in India CMS collaboration, basically CMS collaboration, what we are doing, they also started that thing. So, and that he has another cap, still he is active. He is the author of the PDZ, what you, most of the people you familiar with that. He is the author of that PDZ also. So with this short introduction, I request Professor Gurtu to tell about this collider experiment in India, what he started and presently how it is going on.
Thank you for your very kind words, Govindo. Okay. Well, you see, as soon as somebody is told that you have to give a lecture on history of something, that person has to have sufficiently gray hair. So I, of course, qualify quite well for that. So that is fine. Okay. So, yeah, so I think you already heard this talk on history of particle physics in India. So I'll just go on. Oh, this is the experimental side of collider physics. It's not that in India only collider physics was done for particle physics. There were earlier particle physics was done with fixed target experiments, using nuclear emulsions, using bubble chambers, etc., which actually carried on right up to the 1980s. Okay, but here I will stick to the collider experiments, and actually it's quite interesting. So this is the kind of outline of my talk, that I'll just sort of, just to give a little introduction that, what was known in the 1960s, and just to set the stage. And then we had this participation in this first hadron proton-proton collider, this intersecting storage rings, ISR at CERN. These days, ISR is used for a different purpose, initial state radiation, but at that time one was using this. And then again, little bit of a thing that, during the 1970s, what all got done. And then we come to these 3 experiments in which the Indian groups have been involved. The L3 experiment, the D0 experiment at Fermilab, and then a very comprehensive Indian involvement in the LHC experiments, in 2 experiments actually. So, okay, so here we are. So I mean, just a very sort of one slide introduction. I'm sure you all know this. Okay, in the late 1950s and early 60s, there were a huge number of the particle resonances discovered in accelerator-based experiments. And there were so many of them, they all couldn't be fundamental particles. So in the early 1960s, I think it was 62 or 63, Gelman and Zweig proposed this quark model. Actually, there was another type of quark model also, which was there called Hahn-Nambu quarks, which were supposed to be integer charged. These were, of course, fractional charge quarks. And so knowing that there were these kind of particles, the neutron, proton, and strange particles had been discovered. So these 3 quarks, U, D, and S, they said these are the fundamental constituents. And so they then constitute these particles. And so you had all these sort of known particles at that time: proton, neutron, lambda, sigma had been discovered in the baryons. You had the pi, eta, rho, etc., and these strange particles discovered. And so Okay, so for example, in a very simplest possible thing, you can say that, okay, how does any, this quark, in terms of quarks, how does anything get explained? So for example, this is a simple beta decay of a neutron into a electron and a neutrino. And so, okay, one says that the D quark goes into a U and with the emission of a virtual W and which decays into electron and neutrino. Then, okay, this was the quark parton model as it came to be known. And in 1962, the second neutrino was discovered related to the mu. And during the mid to late 1960s, the theories of electromagnetism and weak decay were unified as a electroweak theory. And it was predicted there should be a neutral carrier also of a weak force, Z0, in addition to this charge carrier, W. Okay. So now we come to this very interesting experiment. Actually, let me say that if you, in fact, try to go on Google, web, and try to say Hadron Collider, you will not even see this experiment or this collider. I mean, you have to actually search for it, saying intersecting storage rings, CERN, and then it comes. But otherwise, you don't even see it. So I think it's good to mention it here. And okay, so first of all, just a little bit of thing about colliders. Well, colliders, as we understand, are actually built to maximize the center of mass energy available. But the problem is that the intensity, because it's just a beam hitting a beam and not a fixed target. But okay, I mean, accelerator scientists, physicists have actually learned to squeeze beams and get high intensities. And actually, the first colliders to be built were in the late 50s and 60s and these were all E plus E minus in Italy, the USA, and in the USSR, Novosibirsk actually. And okay, this thing was the ISR, okay, in the mid 1960s, CERN decided to design a first PP collider so that you could get a high center of mass energy. They had 20 to 30 GeV beams in the proton synchrotron, and so you would end up with a center of mass energy if you collide the two of them of some 40 to 60 GeV. Okay, so okay, this is the layout. So you had the proton synchrotron, and you would just fire protons in one direction. Actually, this ISR ring still exists at CERN. If you go upward toward that restaurant 2 and go a little beyond, on the right-hand side, there's a road going down, and there is still a ring. So if somebody wants, you can actually still see the remnants of that are still there. Okay, so it was very simple. So you circulated protons in opposite direction. There were 8 intersection regions, and the protons collided at an angle of 15 degrees, actually. Well, you can see this here. Oh, these are the 2 rings inside this whole hall. And okay, you have all these kind of things set up here. Okay, so now what was the TIFR experiment? Actually, 3 faculty members, and I must name them, Daniel, Ganguly, and Malhotra. They were in the emulsion section at that time. This is, late 1960s, and they proposed this experiment. I'll just come to that. Okay, I joined just about that time and then became the 4th member of that collaboration. Okay, so the objective was to actually measure the gamma ray production at various angles with respect to the beam axis, and then try to deduce the multiplicity and angular distribution of pi zeros produced in PP collisions at that time highest energy what we actually did at this 44.4 center of mass energy. Of course, ISR would later go on to some 62 GeV center of mass energy, but that happened later. So this was a unique experiment because it was not any counter-based or something. It was just, you just put some emulsions. For those who have not heard what emulsions are, these are just, you may not have even know about photographic film these days, but there were these, photographic film which you use in the camera. So these emulsions were thick photographic films, and like you have photons falling on a photographic film and producing images, if you had charged particles passing through these thick emulsion sheets, they would leave tracks. And so you would then develop them and fix them like you did the old film, and you would then see the tracks. And so you would, use the microscope. This was excellent spatial resolution because these grains which you saw inside were a couple of microns. So you had a spatial micron, spatial resolution with excellent spatial resolution. And so these were used as the detectors for these gamma rays to actually materialize in, and you see the tracks. So it was very simple. So okay, here you are. This is the actual, Okay, this is the schematic setup, as you see. So these are the two beams, and one had these emulsion plates placed at these 4 angles. And here you see the actual place. This is courtesy CERN photograph from 1971. And if you see very carefully, I am standing here, and here's another technician standing there. And these plates were actually placed on this bar, as you can see. This was a trial run, something was put here. Huh?
You were standing there?
Yes, here.
With you?
Yes. Hardly recognizable. Anyway, so okay, it was all right. So I mean, this is what it was. And well, here you are. Here is the paper published, 1973. And this is the spectrum. This is the spectrum of gamma rays. And these crosses here that you see, these are the 4 points measured via our experiment. Okay. And so, okay, this is this abstract, etc., that from 27 to 88 degrees theta center of mass. And we then, deduced the pi-0 multiplicity, and then also on that basis gave some charge multiplicity. In fact, we were also part of 2 other collaborations, which were of the Krakow group in Poland, emulsion experiment, because we had helped each other in taking the exposures, etc. But anyway, so I mean, this was it. So this is the first hadron collider experiment, first hadron collider ever. All right. Okay, and so, but there was actually a lasting legacy of ISR. Because at that time in this late 1960s, this accelerator at Serpukhov, which was 70 GeV proton machine, had actually noticed that the total cross section of proton-proton started to sort of level out. Okay, this is the Serpukhov energy here. Okay, and just about 70 GeV. Okay, this is the P lab. Okay, but it was not quite sure. Earlier, people had observed this cross section going down. But here they observed it is sort of leveling off. One wasn't quite sure what was happening. And then here came ISR. And you can see that you can now clearly see this rise. And then it, of course, kept on rising. These are, of course, much later experiments. But actually, ISR really confirmed the rising cross-sections of proton-proton. Okay, so I mean, that was the ISR, the first hadron collider. And so then what happened meantime in the 70s? Oops. So you have, this we already talked about. And then in 72, actually Kobayashi and Moskva then made the prediction of the 3 quark, that there should be 3 quark doublets and not 2, and 3 lepton doublets correspondingly. 1973, actually, this neutral, weak current, the Z was indirectly discovered at CERN in a bubble chamber experiment. And we all know, 1974, the charm quark was discovered, 1975, tau lepton, 1977, B quark. I mean, you feel jealous of these guys because, every year there was a, new discovery taking place. Unfortunately, we haven't had that kind of luck in the past 25 years, but it was really quite a bit of thing happening here. And then, of course, in the 1970s, with all this thing happening, the electroweak and the QCD theories actually got sort of firmed out, okay, and as we know them. And but what was actually direct discoveries that still remained were that of the W and Z and the Higgs, the top quark, and the tau neutrino. They all remained to be discovered. And they were actually. So 83, 84, W and Z at CERN at the P-bar-P collider. And then you had from the 1989 to 2002, LEP then, and this really represented a consolidation of the standard model actually. And 95, the top quark, 98 neutrino oscillations were discovered with, okay. And well, they were sort of confirmed. They had already been talked about earlier. And in the year 2000, finally, this was discovered in 2012. So this is just a sort of, picture that how the whole thing went. In the year 2000, what one had already was all this had been discovered. So, okay, now before going on to the, LEP and Tevatron and the LHC, just a very generic thing about the generic structure of the detectors, because one wants to detect and measure everything, okay? And you have all kinds of things being produced. You have charged particles, which are produced. You have electrons and photons, coming from the pi zero. You have charged hadrons, which are seen in different parts, etc., etc. So okay, this is a kind of generic kind of detector which has come to be sort of almost standard now. So I won't describe every detector in the thing. So okay, this is what it is. So you start with a tracker, okay, which is inside a magnetic field, so you can measure the momentum of the charged particles to the extent possible with that magnetic field. Then after that, the electrons and the electrons, the things which have so you have a ECAL here, electromagnetic calorimeter, which will absorb the electrons, and if there are photons which will shower inside that, and so these are contained here, and so you will then measure the energy of these here. These are these kind of particles. Following that, you have a hadron calorimeter for the hadron, which will, again, these hadrons will go and shower in that. And so you measure the energy. And finally, then the only things sort of basically left out are the muons, which only interact not very strongly all through. And so they then persist. And you have these muon chambers later on. And you also have this magnetic field. So then combining all this, you will get a good momentum resolution. So I think basically this is the kind of signature that you see for these various kinds of particles. So I think this is basically what one has these days. Okay, so now let's just go to LEP and okay, and so as I said, these had now electroweak and QCD theories and indirect observation of the Z0 at CERN was there in 1973. And as I said, W and Z were discovered in 83. But still, I mean, these were discovered in this PYP collider, but the statistics was not very high. And so one really needed, if you wanted to study details and verify detailed predictions of these theories, one decided to have CERN decided to actually go and build a Z0 factory, basically. And so then CERN went ahead with that. And in phase one, LEP1 would be a Z0 factory with a center of mass energy around 88 to 94 GeV, because one knew that the Z mass is around 90 or 91 GeV. And then LEP2 would then go from 161 to 200 GeV in order to be able to study W plus W minus pair production. Okay, but there's just note that already at that time, the size of LEP, 27 kilometers circumference, was designed to be able to accommodate a suitably large PP collider, and which came actually the LHC. Okay, so here is this whole configuration of LEP, and it was again fed by these various boosters, the synchrotron, and again the electron and positron going in opposite directions. And okay, yes. And the L3 experiment in which the TIFR group participated was here in this intersection region number 2. In fact, interestingly enough, now Alice is there in that same region, and they are still using the L3 magnet edge. Okay, so well, here it is. As I said, this was a kind of, in that sense, generic detector. So you start with this TEC, this tracking chamber inside, and surrounded by this bismuth germanate crystals, which will, okay, this is the electromagnetic calorimeter. And then you have the hadron calorimeter outside. And you try to replicate this kind of a thing in the forward backward direction also. So you had these end caps, hadron calorimeter end caps here surrounding that. And then eventually you had the muon chambers and the solenoid magnet. So you had a magnetic field surrounding the whole detector. This is a typical generic kind of detector. Okay, so then, this was this TIFR group in L3 at LAP. We joined in 1983 and, okay, fabricated brass tube proportional chambers. I'll just show some pictures about that, what exactly we did. And in collaboration with the Aachen 1 group, and I think we played a very significant role in the core software development, and our expert on that is here, actually sitting right here, Sunanda Banerjee, who's also giving lectures here in the school. So I think that was a very, very good, huge contribution. And I think during the LEP 1 period, this group was completely, in fact, responsible for the L3, we had joined the L3 experiment, L3 line shape fits and analysis, which led to the precision determination of the Z mass, width, coupling, which eventually, okay, one got the number of light neutrino species. There were, again, very strong contributions in B physics, and especially to identify them, this neural network kind of things had just started at that time becoming useful and fashionable in this field. And that was a very good contribution. QCD, and again, I think it was very nice, because here you had this, one could actually determine the running of the strong coupling constant, because this was at a much higher energy. So you could actually, and I'll show you the curves of that. And of course, well, there were Higgs searches, which were fruitless because the Higgs turned out to be much heavier. And finally, in the LEP 2, when it came in, I think 1996, one studied this W plus W minus production into hadronic and the semi-leptonic final states. And then the group was involved in the W mass and width determination at the threshold, the reconstructed, etc. And all these things continued, the QCD, 4 jets, analysis, B physics, etc. Okay, so the hardware contribution of this group, and as this is a bit detailed thing. So these are these end caps here, as you see. Okay, HC1 is outside all this. And then inside there are 2 of these things, okay, HC2 and HC3. So that this is HC2, the inner one, and HC3 is this one, which is a little more forward. Okay. So then what did we do? So here you are. Okay, this is, and I am again very thankful to the convener of this school, Govinda Majumdar, for having preserved these L3 chambers. And I just took a picture of that from his office, in fact. So exactly this is what it is. These are just brass tubes stretching inside here of a thickness, 0.3 millimeter thickness. And this cross section here is 5 mm by 10 mm. And the way it acts as a detector is that you have this tungsten, 50 micron gold plated tungsten wire were actually threaded through the length of each tube. And there was a voltage applied between the wire and the outside of the brass tube, and you picked up the signal basically. And of course you have to hold the tubes together, so you had these brass plates outside. And I still remember, I think Sunanda and I had gone to some industry here to get this precision cutting of brass plates, etc. This was, I think, in 1984 or 85 or something like that. Anyway. Okay, so here is this different. Here is this thing, completed chamber, and as you can see, all these tests have been carried out. the HV okay, something okay, okay, temperature control okay, DC thing okay, okay, it has all been tested out, and you see these kind of leads. Here are these kind of nozzles, okay, and the gas would flow. Okay, there was okay, argon, CO2 80-20 gas mixture going through it, and okay, that's what it was. And you had this. So we actually made something like the total number of chambers that we actually made was about, as you can see, around 900 and some spare of another 100. So we shipped all these to CERN, I think, in sometime in 1988. And well, lab was to start in 89 July. So okay, everything was put together and then assembled. Okay. So that's what it was. Okay, here are some of the first papers published by the L3 collaboration. There's the line shape paper. So this is the, okay, and it came very, very quickly after the experiment started, because lab started, I think, in August of 1989, and already within 89, I think this is probably November or something. So the thing had been analyzed, and okay, already it was there. And here is the first paper on okay, this okay strong interaction, this okay coupling. So this is 1990. And as you can see, this actually, sort of fixes the thing, this running of the alpha S, because it is so far away, so you could actually fix it much better. Of course, now the precision is much more, but I mean, at that time, this was actually a very good point to get. And this is the BB bar paper, again, published in 1990. These were the first papers on these three topics which were actually published. Okay, so I'll cut a long story short. I mean, many more things have to be described. So this is eventually what came out, okay, combining the results from the 4 LEP experiments, Aleph, Delphi, L3, Opal. I mean, mass of the Z was determined to an unprecedented precision not seen so far, okay. This is 1 part in 45,000. And it took into account, in order to get down the systematic errors, you see, if you want to know the mass, you have to know the energy of these beams very precisely. And now what all can affect it? Earth tides. Okay, because you have heard of ocean tide, but earth tide I had not quite heard at that time. But it seems that due to the moon, even the crust of the earth little bit undulates. And so the circumference, 27-kilometer circumference of LEP could change by a few millimeters or something. And so that was taken into account. Then you had these trains running nearby that. And so you had the electric train, and so some low intensity currents would be flowing, which would go in the accelerator and would cause some disturbance. That, so the train's timetable was used to sort of try to correct for that. It was really quite a thing that was done. No, that is why you actually got this kind of precision. Okay, I'm 2 MeV in 91 GeV. And so here it is. And this whole thing led to, of course, also this number of species of neutrinos. Okay, because you then determined all these, widths, etc., so precisely that, as you can see, that if you had 2 neutrinos, this would be the curve, 4 here, and you have this 3, and you can see all these things just fall precisely on that. And this error bar that you see here have been increased by a factor of 10 just to make them visible here. Okay. So it was that kind of a precision experiment, and it was really very successful. Okay, then I'll just describe very briefly. LEP 2, of course, went to W plus W minus cross section. And again, you see verification of the standard model. Here is the standard model prediction, this blue line, including all the thing. And if you, for example, did not have this vertex or only some exchange was there, they all don't fit at all. So this thing actually just showed that the standard model works, okay, completely. Okay, and over this whole range of energy. And here is this LEP, okay, W boson mass, which came out, and of course the limit on the Higgs, okay, greater than 114.4 GeV. This was the most sensitive thing at that time. So as I said, I mean, just to summarize, the overall impact of lab physics was vast. It led to a, really a precision testing and vindication of the standard model. And it set a new limit on the Higgs mass. No new particles were discovered, and it was a bit, well, that story has continued. So I mean, okay. So all in all, by the end of the lab era, the standard model stood well entrenched. Okay, now D0 at the Tevatron. Well, here's the Tevatron picture, and the position of these two experiments, D0 and CDF. And again, these are the various inside components, this silicon detector, the central calorimeter, and the trackers. These are, some of the important components there. So we'll come to the Indian contribution. So these three groups were in D0, joined at slightly different times, I think. And the TIFR group contributed significantly toward the hardware. All three groups participated in the running of the experiment and in data and physics analysis. And apart from extending the study of p-by-p interactions, actually the main highlight of the Tevatron was actually the discovery of the top quark in 1995, which completed the quark doublet, triplet. And and in fact, these people from the Punjab University, in fact, had worked on this top quark search at that time, and owing to much larger W plus minus statistics available, they actually determined the W mass to a higher precision than LEP, and we'll come to that a bit later. Okay, so the hardware participation actually came from the TIFR group. They actually joined in 1990, a bit late, because the Tevatron had already started in the mid-80s. I think 86 or 87, it actually started running. And they actually participated in this, hardware, in the design of the central muon scintillator detector, the fabrication of these muon scintillators, performance studies of the pre-shower detectors, many other contributions like the calibration of the scintillator PMTs, etc. And here are some of the pictures from that time. This is the detector fabrication in TIFR, and you can see all this thing taking place. This scintillator detector, and then participation in D0 physics. Top cross section measurement, B physics, Higgs searches, and of course searches for and actually many students were trained on this, as were on the L3 experiment. Okay, I mean, since this top was the highlight of the Tevatron, this is an example of an actual TT bar event, and the top, of course, decays predominantly or only into W and a B, and so you have two jets due to W and two jets due to the Bs, and very nice picture actually. Okay. And this is a detailed explanation of this, for example, but I'm not going to go through all this. Okay, so you have this, two jets identified by a silicon vertex detector from the bottom anti-bottom, and there are then jets coming from the quark decays. And we have seen that, and you have the multiple jets along with the positron alert experimented to the possible creation of a top, etc. And so anyway, this whole analysis was done, and so the quark, the top quark was then discovered, and these are the publications actually. This was in 1995. This is the D0 collaboration, observation of the top quark, Abachi et al. This is 1995 PhysRev letter. And they actually use this variable, the HT, which is basically just the scalar sum of all the energy going in the transverse direction. I mean, again, these, hadron colliders, you don't have information on the, or you don't know what is the collision energy of the partons. So you can do things only in the transverse plane. And so okay, this is a very good variable, and this is an excellent signature for the TT bar production. They actually observed 17 events with this kind of signature, and expecting a background of about 4 events. And so this was their first determination of the top mass. Okay, so well, here we are. So then CDF discovery was also there, and okay, here is that paper, also 1995. And okay, I just for the completeness, the current best value of the top quark mass is actually now gone to two decimal places, 172.69 plus minus 0.30 GeV. And again, just for completeness, I'm mentioning that in the year 2000, this tau neutrino was also discovered, which actually then led to the completion of this whole set of standard model particles and these force carriers. Okay, and of course, this Higgs was still to be discovered after 12 years in 2012. Okay, let me just mention as an interesting sort of footnote, the discovery of the tau neutrino, by the way, also used nuclear emulsion pellicles, because as I said, that had the highest resolution, and so you actually fired neutrinos into these, and then try to see if they actually produce some electron or muon or tau, and so you could actually track it in that. So I mean, it was quite interesting. I mean, this was this use of emulsion as a very high resolution particle detector still continued. I mean, even up to the discovery of the tau neutrino. Yeah, this is the so-called donut experiment, and they actually published in the year 2000. Okay, I am just going to spend a few minutes here on. I'm sure many of you may have heard of this new controversy, if you wish, this W mass. Okay, we saw that Lab produced this accurate value at that time using something like 40,000 WW events. With all the 4 experiments. Now the advantage, of course, is that being an E plus E minus collider, the initial energy momentum is completely known, so you can apply this conservation and then properly reconstruct the W mass. Now in any hadron collider experiment, when you detect the W, again you only do really meaningful measurements only in the transverse plane, and so you have to deduce the W mass, and you have to go through modeling and fitting of the measured energy momentum distribution in the transverse plane. Okay, for example, this is from this recent paper. So you can, for example, measure the transverse, or you can calculate the transverse mass of the W using the missing PT of the neutrino in the opposite direction. You can then measure the PT of that lepton, and you can then get this. This is from the missing PT, and so this is for the muon, and this is for the electron. So that this is how, using these distributions as sort of templates, you try to fit the W mass in the best possible way. So it is a little roundabout way. It is not a direct reconstruction of the W. So basically, it's that. Okay, so now I'm not going to go in any further detail. Just show you this one slide. So here are all the data from. This is LEP. This is this LEP average. Okay, up to March 2022, you have the CDF result. You had the D0 result. You had a Tevatron average. Then Atlas at LHC produced this result, and LHCb with rather larger errors had this. And so you got an LHC average, and this world average turned out to be 80.377 with a 12 MeV error. And all these are sort of consistent with each other and with the standard model prediction. If you exclude the W mass and you fit everything else, all the other data, you actually get out or something which agrees with this within some one or two standard deviations. In April 2022, the CDF, using their full data of some 4 million Ws, came out with this extremely accurate value, which completely disagrees with the earlier world data as well as with standard model prediction. And it has this extremely small error. Actually, that is the real thing. Okay, because 9 MeV error makes everything, the discrepancy completely magnified. Okay, so how do you even sort of combine this kind of discrepant data? So, okay, just for information that right now there is a combination group of physicists from all these hadron collider experiments, CDF, CMS, D0, ATLAS, LHCb, trying to go over various inputs that go into their W mass and other people's W mass, etc., and trying to figure out what could be the problem or not be the problem, or what. Okay, this is a sort of unsolved issue as of now. Let's see what happens. So it's quite exciting still, actually. Okay. Okay, then Tevatron also searched for non-standard model particles beyond the standard model in terms of the minimal supersymmetric model, this 2 Higgs doublet with some mixing angle tan beta, which leads to 5 Higgs particles. 2 of them are charged and 3 of them are neutral, and they they put limits. Here are some of the papers. Similarly, for search for the supersymmetric quarks and gluinos. Okay, then second generation lepto quarks. I'm just sort of showing you that, what all was sort of searched. All kinds of searches were made as they have been made at LHC, and the result was basically nil. Okay, so then LHC, so then post 2000, the only standard model particle remaining to be discovered was the Higgs. Additionally, from various sources, one felt that some new phenomenon, some new particle should be discovered in around the TeV mass range. In particular, this SUSY supersymmetry conjecture and theory developed around it was actually very attractive. And the conjecture was that for every particle in the standard model, there should exist another set of particles differing by half spin. So the quarks and leptons, which have a half integer spin, would have counterparts of supersymmetric quarks and supersymmetric leptons with an integer spin, etc. Okay. And to me, actually, the great plus point was it had the potential of accounting for the dark matter, which we all hear about, which was discovered in a totally unrelated field of experimental astronomy 80 or 90 years back in the 1930s, from the rotation of stars around the center of galaxies. Okay, so that this was actually very attractive because some of the supersymmetric particles like the so-called neutralinos, etc., could actually explain that. Okay, so now we come to the LHC finally, and so it actually started in 2008, and it had a sort of not a very propitious start. Something exploded inside one of the places, and everything was shut down for a year and a half, and people were very depressed, etc. But in 2010, it came up and has been running fantastically since then. And so at that time, then they were very careful because the design energy was, of course, 7 TeV per beam, total center of mass energy 14 TeV, but they were very careful for the first 2 or 3 years, and they only operated at 3.5 and then 4 TeV per beam. But they still did good physics and actually discovered the Higgs in that. Then from 2015, after the first shutdown, they actually went up to 13 TeV. And as of now, they actually run at 13.6 TeV. And this is where you have all these 4 big experiments there: ALICE, ATLAS, LHCb, and CMS at the furthest 0.5. Okay, this is, I must say, LHC is really a technological marvel. You have these, well, it's the coldest place in the universe. because inside it is maintained at 1.9 degrees Kelvin. And please note that outer space is at 2.7 degrees. That is at microwave radiation. So, I mean, it's really the coldest place. It's also the most empty place in the galaxy with extremely high vacuum, so that the beams don't dissipate. And okay, I'll just go now straight into this. Okay, India is in 2 LHC experiments. So Indian groups participate in this CMS and in ALICE. So CMS is one of the 2 general purpose experiments at LHC. ATLAS is the other one. ALICE is a specialized experiment for studying nucleus-nucleus collisions in search for QGP, where they have found good signals, etc. Okay, India CMS has this institute, TIFR, as its nodal institution. India ALICE has this Variable Energy Cyclotron Center, VEC, as its nodal institution. Okay, I'll just first go over ALICE quickly, because I am not going to discuss too much physics in that. Okay, where they have contributed are actually two detectors. One is this photon multiplicity detector toward one side, and on the other side there is this muon detector. And there are many stations to take the signal of muons as they then pass through and then get their momentum. And so I'll just come to a little bit of detail on these. So these are the groups in ALICE. There are quite a number of groups now. The 1, 2, 3, 4, 5, 7, 8 groups here. In this detector and in this muon system, there are only 2 groups actually. Okay, so that this is the structure of this photon multiplicity detector. So they have this is some kind of honeycomb proportional, honeycomb counters, kind of proportional chambers, proportional counters. And in order to distinguish between this passage of a hadron and if a photon is going through, they actually have a pre detector kind of thing here. And so if you get a signal here also, then you say that would be a hadron. So you actually reject that. So a photon would pass through that and then come here, and you have a converter, photon converter here, and so it converts and then it showers in this part, and you have these structures, detectors here, and so you can distinguish between hadrons and photons, and also localize the photons pretty accurately because of this kind of honeycomb structure inside. And so you have 2 halves. I'll just show you the whole layout in the future. And so you have these 2 planes of honeycomb proportional counter. These have some 3 radiation length of lead converter and arranged in these 2 halves. And it is installed at some 3.6 meters from the intersection point. And so this is how this whole thing comes together. These are these two halves come together like that. You have this kind of super modules here. And and so each module has this some 4,600 cells, and you have these PCBs, etc., to then take the signals and convert them and so on. Very briefly, this is this forward muon spectrometer of ALICE. There are 5 stations. Beginning with the first one, which is closest to the intersection region, and India is the Indian groups are actually responsible for the second station, the station 2, tracking station 2, and also part of the absorber, because this in the forward direction they actually want to then absorb the strongly interacting particles, and they also have then produced this readout chip for all the about 1 million channels in total for the muon system. So here is a view of the muon chambers which have been installed there actually. You can see them. And basically they have then tried to study this QGP formation in these heavy ion collisions at these high energies. And so they try to study these kind of resonances which are there, quarkonia, and try to deduce things from that. And basically these are this earlier known these, okay, vector mesons rho omega phi, then you have the charm anti-charm thing, and the BB bar upsilon states here. Okay, this is the additional contribution from this group. Yeah, this is front end absorber components, as I said. So you have the graphite core. All this was actually completely done here in India and then transported to CERN. So here, okay, they actually have this. So the hardware summary, the R&D for a special honeycomb proportional counter with a zero crosstalk for charged particle detection. As I explained, that you actually have this veto of that. And they made these large-scale gaseous detectors with hundreds of thousands of channels made for Alice PMD and the muon tracking stations. And you had this low-noise analog signal processing ASIC designed and fabricated, supplied to a major internet. And it was supplied not only for the Indian detectors, but for some other detectors also. So I think this was a sort of major success story, in fact. Okay, now I come to the India CMS collaboration, and in which also, by now, I think there are some total of 14 groups. To start with, there were 5 groups, 2 from TIFR, one which had been in LEP and one which had been in the D0 experiment. And there was this group from Punjab University. And then there were two groups, BRC Bhabha Atomic Research Center and the Delhi University, which were responsible for the silicon pre-shower detector. And I think both of them were the physics necessity was to ensure a more hermetic detector to look for missing energy signals, for example, SUSY or other particles. And this pre-shower detector, physics-wise, it was important to distinguish again between this gamma and pi zero to detect the Higgs to gamma decay, which was used actually in the final analysis. Later on, there was also 2011 to 13, the RPCs were also fabricated, and 2 of the groups, the BRC and the Punjab University, contributed to this effort. And these were installed in the 2013 to 15 shutdown. I'll just show some pictures of these things actually. So, here you are. This is the CMS detector, the open view, and you had this. So you had this pre-shower detector actually, as you can see right here in front of the calorimeters here. And this outer hadron chamber, I'll just show you in the other slide. Okay, here you are. Here is this other cutout view of the CMS detector, and here this is where the outer hadron calorimeter was put. Actually, what was realized? This is this inner hadron barrel calorimeter, and it was realized that this particularly in this direction, in this the amount of absorber was actually not enough. It was something like I think 8 or 9 interaction lengths, but they wanted more, and so they thought that you can use this this part of the magnetic coil, etc., as a part of the absorber, and then you have this detector outside which can again detect the hadronic signal here. And so these 2 layers were here. It's outside the solenoidal magnet, basically. Okay. And so this basic design was this detector element is a plastic scintillator tile which then produces light when a charged particle passes through it. It's collected by embedded wavelength shifting fibers. I'll just show you those. And the light is then transported to a HPD detector via clear optical fibers. And the size and placement of these tiles is actually matched to the geometric towers in the CMS calorimeters. They are grouped together, and then for ease of handling, I'll just show you that. Okay, so here it is. Okay, this is one tile of scintillator, and you see these grooves inside, and these are this keyhole grooves, which mean that that you then insert the fiber from here and it goes all the way in, and you do that, and so there are 4 fibers inside each of these scintillator plates, and they all four of them come out from here, and you place these tiles side by side, and you take out all these fibers, and then they actually make them into what is called a pigtail, and the signals are taken out, and you group them together, and then you can put them inside this whole finished tray, which has to be inserted inside that. Okay, so then here you are. These are these trays in these frames being actually installed inside the CMS magnet, and you have this another view of that. Okay, these are all these outer hadron calorimeter, these trays which have been installed. Okay, this contribution was the silicon detector made in Bangalore on a micro module made at CERN. And so these were the things that were actually put there. These wafers we actually got from outside. I believe there was Hamamatsu wafers, silicon wafers, and this whole assembly was then done here in Bangalore. And as you can see, this is, then they were placed inside this end cap. There's the mounting being done at CERN, and then the whole thing was positioned in place. And this is that later thing of this, RPCs which were made. And okay, I won't go into the details because there's not too much time actually left now. So we had this. Okay, here was this workshop set up at DRC, and then people from the other group came and sort of helped out. So this is all the assembly taking place, and the fully assembled RPC and being installed in this end cap region in the CMS. So I think that is that was the kind of hardware contribution that was made. And now I'll just very quickly just summarize this the discovery of the Higgs, because this is really what has the last missing piece of the standard model that was discovered there, and which had been searched for. So of course Higgs can decay into any of these constituents, and Higgs in principle at the tree level cannot decay into a gamma, because it couples to mass basically. So the rate is 0, but indirectly it is possible. And in fact, the Higgs can go through this kind of a diagram of this, T loop or a W kind of loop or something, and it can then go into Higgs going to gamma decay. It is not a very frequent decay, but it has a very clean signature, because you have these two gamma rays coming out, which can be detected very well, and their energy can be very well measured, and so you can then get the effective mass from there. And so that's it. I mean, you have then you detect two gammas with energies E1 and E2 with a width with an angle theta between them, and mass of the Higgs is just this. I mean, that's what it is. This is simple effective mass formula. And of course the gammas can come from other sources also, so they'll form some background, and you could have pi zeros decaying and so on. And so if we then plot 1m, plot m, then you will see a kind of continuous distribution of the background. And if a Higgs is present, one will see a superimposed peak. And here is the discovery papers of these two collaborations, Atlas and CMS. And this is CMS. And again, you see this, I mean, completely, this is that 7 TeV energy, basically. And you had, even at that time, this was 2012, so one got sufficient statistics that you actually saw this thing completely like that, and you see this peak here. And similarly for Atlas. So that was the, long awaited and long search for Higgs boson. And of course, we all know then next year, Peter Higgs and Okay, who's the person still alive out of the other? Yeah, two of them actually got the Nobel Prize. So okay, so now these are the they also saw the Higgs in this Higgs going via a Z and a virtual Z sort of into eventually four leptonic decay, and you see this some little peak here is the Z peak actually, and you see this peak here. Similarly for Atlas, you actually see this little peak, but as you can see at that time, this statistics was not that good, in fact. So now I just show you for completeness. This is as of 2022. Okay, published, and you see this beautiful on the basis of 13 TeV 138 inverse femtobarn integrated luminosity. You have the beautiful peak of the Higgs and so on. This is the gamma. This is this 4 lepton, and you see this very nice peaks and so on. Okay, similarly for Atlas, and so and you see the Higgs and then other decay channels also. Tau now you're beginning to see it, and mu again. Well, okay, you can see something. Okay, and as of now, as I said, these are the best values of the Higgs mass available, and work is now again now it is going on, and okay, so I think I sort of come to the end of my talk, and so now what now? So as we have seen, no new physics beyond the standard model has been discovered, either as a new particle or a deviation from its prediction. No serious deviation is there. Of course, LHC is going to continue till around 2035 or maybe 1 or 2 years beyond that, or with of course successively increasing luminosity. But there is no increase in energy that is envisaged, and so any deviation from the standard model will have to be discovered via some very high statistics studies of various processes, and then comparing them with the standard model predictions. But this is actually this seems to be a very sort of unique situation in particle physics, because this 60 years back in late 1950s and early 60s, people didn't have a theory, but they had at least many particles being discovered, and so people sort of thought of some theory or some model. This quark model came up, and then slowly this theories developed, and from the 1970s, actually experimental particle physics has basically been driven by the predictions of the theory. Kobayashi Maska said there should be three generations, and so you then said, okay, let's see, and then you actually found you found the tau lepton, and then you found the B quark, etc. Then W and Z were supposed to be there, and you then discovered them, and very good. So again, some more consolidation. Then the top quark was discovered, the tau neutrino, and now the Higgs is discovered. But but now the standard model doesn't. Whatever standard model had to predict has been predicted and already discovered experimentally. So now, of course, one could say, well, standard model is the last word and that's it. But that's not quite true, because there are outstanding problems. You see, on the experimental side, as I said, you have dark matter. it has to be something. Okay, this is, it's there. Okay, and this is, and it came from a totally different, astronomical observations. Okay, and then you have, of course, non-zero neutrino masses. which again in the standard model per se, these masses should be zero, but they are non-zero. So, okay, from the theory point of view, the standard model doesn't seem to be a fundamental theory. I mean, there are too many arbitrary parameters. Okay, all the masses of all the particles are fed in by hand. Okay, number of generations of what you have experimentally discovered, they are there, but why? Okay, okay, you know, etc. I mean, okay. So I mean, right now, that's where one is. And so I think, I mean, basically one has sort of reached a stage that, you know, experiment has to sort of lead the way to, you know, find something different. So otherwise, okay. So then what are the things possible? Well, one, of course, is LHC is going to continue. So that's there for another 12 years, 13 years, whatever. And there have been many discussions on these possible future accelerators, and the International Linear Collider, this future circular colliders, and the Chinese electron positron proton collider kind of things, and but nothing concrete has as yet come up. But I think maybe something will come out of extensive study of neutrino physics. I mean, because that is a, you know, little different kind of thing, and because neutrinos interact very weakly, it takes time, and there are now new experiments, the Dune, etc., are coming up. Maybe they will show something. But right now, it's a sort of, it can be termed a very interesting situation, or it can be a sort of strange situation, which it is actually. So anyway, I will just leave it at that. And yeah, thank you very much, and thanks to the organizers for allowing me to talk about all this. Thank you very much.
Thank you, Professor Gupta. Taking us this memory lane of the old many things, old memory. Just one thing I said that the left, this is the circular ring is bending. Was it that Lake Lemon, this water level increased? That's why that pressure it's changed the.
Maybe they even took that into account. Okay, I don't know. No. But those two things I know.
Yeah.
The earth tides, the effect of the moon. Okay, because the earth little bit, you know.
Yeah.
Okay.
And the train
and the railway
TGV,
track.
that's
No,
that
sure, for sure.
Yeah. So any more questions? No?
Yes, Sunanda had a question.
Just, I think we also participated in the Bell experiment, okay, from India.
Huh?
Bell experiment.
Bell experiment. Yes.
So
Yes, left out. Yeah, okay. Yes. No, okay. Partly also, I think. Yes, it was. Okay, quite a lot of things here, and yeah. No, Bell experiment was there, and I think a number of people have done from TIFR and from.
Now on the many
some other
institute also
experiments.
there.
Yes.
Okay, sir. Sir, your first point in the slide, you say no new physics beyond standard model has been discovered. So what is your comment on this neutrino oscillation? Because it happens due to this mass difference of this masses of this neutrino. So what is your comment on that?
No, sorry.
This neutrino has
Yeah.
masses, we know. In the standard model, we say they are massless.
Yes.
So this is neutrino oscillation is new physics, right? So what is your comment?
On the mass oscillation of neutrinos.
Yeah.
Well, okay, there are, see, okay, in the standard model, they are supposed to be zero, so there should not be any oscillation at all, okay? But oscillations are there.
Yes.
So, okay, there are models, okay, but but the point is that, that otherwise, okay. What I've also seen somewhere is that if you take the standard model and you say that we will put in, after all, you are you are putting in the masses of all the other quarks and leptons
Yes,
from
yes.
experiment.
Yes.
If you also put in the masses of the neutrinos, okay, once you determine them, well, that is the whole story. I mean, for the time being. No, but again, you see, dark matter is not explained at all. Okay, that's not there. And so you have to then do something. I mean, you don't know what to make of it. No, all I'm saying is that you are in a kind of situation where there are, these indications have been there. I mean, that, neutrino, non-zero mass, and dark matter, these are very strong indications that there is something beyond. But then whatever one could think of, people have predicted, nothing has been found up to now. I mean, that's where we are. And basically, it's that.
Anything more? Okay. If not, otherwise, I'll just thank Dr. Gurtu for the excellent talk and give a small painting.
Oh, thank you very much.
Local people and the art collection.
Oh, wow. Okay. No, this is okay. Thank you very much.
Okay.
Thank you.